right, hello everyone, and welcome to the first Astronomy on Tap of the new year. We are really excited tonight. We've got Dr. Troxel from Duke University here to talk about cosmology and gravitational lensing, which is sure to be an excellent talk. We are very much looking forward to it. We're going to let Dr. Troxel get started in a little bit, but before we do, while we're waiting for everyone to sort of trickle in, I have a couple trivia questions. Um, for the first of our trivia questions, and you could just go ahead and throw the answers in the chat on YouTube if you want, we have, how old is the universe thought to be? So I'll give everyone a few minutes to think about that or look that up if you want to. Looks like we've got a couple answers pouring in. Hello to Fred from Connecticut. But the answer to this one, as you may know, is 13.8 billion years. That's the approximate age of the universe. The others ages that I stuck in there are all different ages of various things. 4.6 billion years is about how old the sun and the rest of the solar system are. 13.5 billion years is an estimate of the age of the Milky Way. And then 10 billion years is an estimate of the age of the Andromeda Galaxy. For the next trivia question, we have, what did astronomers learn about the universe by observing distant galaxies? So it's shrinking, it's curved, it's finite, or it's expanding. All right, I saw some answers in the chat. For that one, looks like Eric Peterson got it right. D, the universe is expanding. Yeah, so that was discovered. Astronomers looked at some distant galaxies and saw the Doppler shifts of them and determined that the universe is expanding. For our last trivia question before we get started with the talks of tonight, I have, what is the name of the giant galaxy supercluster discovered in 2014 of which the Milky Way is part? So this one might be a little bit more difficult of a question for some of you, but I'll leave it up and give you a little bit of time to come up with the answer. Yeah, I saw a few answers in the chat. I did see one person got it right. The answer is the Laniakea supercluster. So the Ursa Major cluster is a cluster of galaxies nearby, but it's not a supercluster. Group 82 might be a thing, but I just made that up. And then the Shapley supercluster is a similar supercluster to Laniakea, but it's not the one we're in, it's a neighboring one. So Laniakea is a really super giant cluster of clusters of galaxies. That's very cool. There's a really neat YouTube video about it. It's just a couple minutes long if you're interested. It's one of the first results if you Google it. But yeah, and that is the end of our trivia for tonight. So I'm going to get started with the intro talk before I hand it on over to Dr. Troxell. And if you're familiar with Astronomy on Tap Triangle, you know that usually for our intro talk, we give a little introduction to what the speaker is talking about, in this case, cosmology and gravitational lensing. But tonight we're going to shake it up a little bit. In honor of Black History Month, I'm going to be talking a little bit about some really cool research done by Black astronomers in the last few hundred years. And so I will get that started. I'm going to start with a little bit of a disclaimer that I'm going to talk about 4 different astronomers, which is barely scratching the surface of excellent research done by Black astronomers in the past couple of hundred or even longer than that years. And I am going to focus mostly on American astronomers and astronomers who did what I would consider sort of traditional astronomy. So they studied stars or planets, or they built instruments to study stars and planets. And not things like astronautical engineering, things that a lot of Black women were involved in the computing of orbits and things like that for NASA. You might have heard about that through Hidden Figures. But I'm going to focus more on what I might consider traditional astronomy. I've made a bit of a completely arbitrary distinction there to narrow down the number of people I could possibly talk about. Starting off with who was probably the very first Black astronomer in America, we have Benjamin Banneker, who was born around November 9th, 1731, in what is today Maryland. So Benjamin Banneker, he was born to a free Black and a freed slave. So he was a free Black man in the colonies. He created and published multiple almanacs, including calculations of solar eclipses and planet positions. And he also was involved in some of the survey work for the original layout and design of Washington, D.C. For that, he probably took astronomical calculations that he used to calculate latitude and longitude positions so that they could do the survey. He also, he was a Black man in a time in which many Black people in America were considered property or were considered lesser than white people. And he talked a lot about that too. In one particular instance, upon receiving a review of his work that emphasized how great it was that this was coming from a Black man, he reportedly responded that he was annoyed to find that the subject of his race was so stressed. The work is either correct or it is not. In this case, I believe it to be perfect, is what he reportedly responded to that review. And he often contained in his almanacs letters or essays on the abolition of slavery or the benefits that should go to Black people, things like that. So he was really, an outspoken advocate of Black people for his time, as well as being an accomplished astronomer. But I am going to focus more on his astronomical work. And his almanacs included calculations of the motions of the sun and moon, the true places and aspects of the planet, the rising and setting of the sun, place and age of the moon, and etc., the lunations, conjugations, eclipses, judgment of the weather, festivals, and other remarkable days, as listed in the table of contexts for one of his almanacs. I've got here a couple of pages from one of his almanacs for the year 1793. You can find these on the Smithsonian website. You can see that he calculated all of the eclipses which would occur during the year, a few lunar and a few solar. He calculated both total and partial eclipses and ones which would not be visible from where he was in Maryland. He also calculated the positions of the planet of all of the planets throughout the whole year, and the lunar phases, as can be seen in this page. This shows April's positions of the planets and the phases of the moon. This isn't really work that astronomers do a lot of today. We have computer programs that we could use to calculate this type of thing much more precisely than we could do it by hand. But back in the 18th century, this was really important work for astronomy. It's incredibly important to know where the planets are ahead of time if you need to observe them to study them, so you know where and when they will be visible. And knowing when the eclipses are, so you can study those. These things, they're vital to being able to observe those objects. So he was probably the very first Black professional astronomer in the United States. The next astronomer I'm going to talk about, jumping ahead quite a number of years, Harvey Washington Banks was born in New Jersey in 1923. He was the first Black man to earn a PhD in astronomy specifically in the United States, which he did at George Washington University, where he worked as a research assistant while he earned his degree. And then he taught as a professor at Delaware State and Howard University, and researched high-resolution spectroscopy and orbital mechanics. So one of his main research focuses was high-resolution spectroscopy. His thesis was titled "The First Spectrum of Titanium from 6,000 to 3,000 angstroms." I have here a spectrum of titanium showing just that range which Harvey Banks studied in his thesis. So in his thesis, he studied sort of this range from here to here, 300 to 600 nanometers or 3,000 to 6,000 angstroms. You can see there's a lot of really interesting stuff going on in the spectrum of titanium across that region. And then in later work he published, he studied actually the full range that's shown on this plot here, which is not, unfortunately, for one of his works. I could not find good images of either his thesis or some of his later publications. Um, but these show all of the interesting spectral features that show up in a spectra of titanium. Work like this is really important, identifying exactly where and what the lines from each individual element are, because when astronomers look at something that's not made of an individual element, but of many, many different elements and compounds of those elements, in order to be able to tell any of what's going on in that mess of lines from oxygen and hydrogen and titanium and compounds of all of those things, we have to know exactly what each individual compound and element does. So this is sort of really fundamental work for understanding the composition of stars and planets that we do today. And this is work that Harvey Washington Banks spent a lot of time on. The next astronomer I'm going to talk about is George Carruthers. He was born in 1939 in Cincinnati, Ohio, and then earned his PhD in aeronautical and astronautical engineering from the University of Illinois in 1964. He then went on to work at laboratories at NASA and associated places and worked on creating the first UV spectrograph, which was used during the Apollo 16 mission, and then several other cameras for use in NASA missions. He was responsible for some of the first observations of interstellar molecular hydrogen from space, which was a very important discovery for our understanding of the space between the stars. And in addition to his work and research, he created and worked with a number of outreach programs around the Washington, D.C. area. So here is the abstract from one of his papers. It's called Far Ultraviolet Imagery of the Orion Nebula. So this is a paper which he wrote analyzing the ultraviolet light coming off of the Orion Nebula, which was photographed using an instrument that he built. So what he found here was that a lot of the ultraviolet light was being reflected around in dust. So we learned a lot about dust in space by being able to look at the Orion Nebula in this ultraviolet light, which we had never been able to do before we had spectrographs that could detect that kind of light, and we're able to launch those into space. So that's what his work, some of his work, he published many, many papers over his long career, was on learning about that dust in ultraviolet light and giving us new insight into dust in star-forming nebulas and things like that. And then the last astronomer I'm going to talk about today is Arthur Walker, who earned a PhD in astrophysics from the University of Illinois in 1962, and then worked in industry at the Space Physics Laboratory before becoming a professor of applied physics at Stanford, where he eventually led the astronomy department for several years. So he worked mainly on the development of X-ray and UV cameras and telescopes, and on studying the solar corona and chromosphere. So this is the cover of the Science magazine in September 1988, and it shows one of Arthur's first images of the sun, using one of the telescopes which he helped to build. His work on the stellar corona, which you could sort of see around the edges here. Stellar coronas are really interesting objects, which are the sort of the hottest part of a star. They're much hotter than the surface of the star, even though they are further out, the outermost layers of the atmosphere. So they're very interesting objects. We've learned a lot about them in the years since, but pretty much all of that was made possible because of the foundation and the instruments which Arthur Walker helped to develop in X-ray and UV astronomy and looking at the solar corona. Yeah, so these are some excellent Black astronomers that I wanted to discuss a little bit of for Black History Month. But now I will hand it on over to Dr. Troxell. Dr. Troxell did his undergraduate at the University of Oklahoma, then before completing his PhD at the University of Texas in Dallas. He now is a professor at Duke, where he studies cosmology using the Dark Energy Survey. So I will hand it on over to Dr. Troxell. You should have sharing. Cool.
Okay, hello everyone. Hopefully you can see the slides now and not my desktop. So I am, as McKenna said, a cosmologist at Duke University. I'm coming to you live from Duke in my dining room right now. And what I spend my days doing as a cosmologist when I'm not on Zoom calls is thinking about a bunch of stuff that makes up the universe that we've never actually seen. And we do this, the way that I work on this, trying to understand this stuff, is through using gravity itself. In particular, a technique called gravitational lensing. So as an intro, here is an example of an image that we take with our survey, in particular the Pinwheel Galaxy, which is a very famous galaxy. But in my work, I'm definitely not an astronomer. I really don't care so much about these really beautiful galaxies, although the images are very pretty. The stuff I care about is the stuff that you can't see in this image. And so in the talk tonight, I'm going to talk about basically 4 questions. The first is to describe to you what it is we're actually looking for in the dark in these images. And then 2 questions that you should immediately ask me. The first is, why should we care if we can't see it? And the second is, how do we see it? And hopefully you'll come away at the end of the night understanding those 2 questions. And then at the end, I want to come back to what it is we do with this stuff in the universe that we can't see in terms of our underlying cosmology mission in the surveys that I work on. So first, I'm going to tell you a bit about how we do this stuff, in particular the dark energy survey that I work on. So the dark energy survey was a 6-year, it was extended for a year from 5, a 6-year observing program out of the Blanco telescope in Chile, which you can see in the bottom right of the slide. There's someone sitting in the chair in the bottom left to give you a scale of how large the telescope is. And with the Blanco telescope, we constructed a camera called DE-CAM, the dark energy camera, which you can see in the upper right to do our observations. And if you look at the shiny rectangular things inside the center of that device, those are CCDs, charge coupling devices. And a CCD is exactly what you would find, though much smaller and less sensitive, in your phones, your phone cameras. So this is just a really big camera made up of about 70 of these CCDs. And so we can use this camera to see basically take pictures of about 3 square degrees of the sky at a time. And an example of that, showing the Small Magellanic Cloud, is what you see on the left, where you can really see all of the individual CCDs that make up the camera in this kind of characteristic hexagonal shape. So the survey is made up of a lot of people. We're funded primarily by the Department of Energy and have about 500 participants, scientists that participate in the science of the survey, coming from around the world. The project that I'm leading right now in the Dark Energy Survey is really an international effort. And this is kind of a random sampling of where the people that are involved in this particular project come from around the world. So we really have a very international and diverse group of scientists working to understand these dark mysteries of the universe. If you want to learn more about the science that we're doing beyond what I talk about tonight, you can follow this hashtag, #ThisIsDES, on Twitter, where we've posted updates about what we're doing and the people that are involved in the survey. I mentioned that this was a survey that lasted for 6 years. About a year ago, the observing part of the program ended. We took our last observations. And this image is an image of the control room of the Blanco telescope, where we control the observations that happen for the people who are actually at the telescope in Chile. And this image was taken during the last image that the telescope was taking on the last night of observations of the program. And if you look at the laptop on the desk that's pointing toward the camera, these are a bunch of people in DES, but on the laptop you'll see a Zoom call that included about 50 of us from around the world calling into the control room to kind of celebrate this last night of DES. And so the survey is over, but the science is really only just beginning. And that's what I want to get to in this talk. So what we did with the survey is we took lots and lots of images of the night sky, covering this area. So this is, you can think of this as the inverted sphere of the night sky. And this black outline is the area that we took pictures in. And what we did is we took basically 10 images overlapping at every point in this footprint. And at the end, we were able to create 10,000 images that were about 0.75 degrees squared. And so each of the tiny squares that fill this footprint represent those 10,000 images. And if you were to take a small region of one of those 10,000 images, you would see something like this, where you have this background field of many galaxies. There are hundreds of galaxies in this image. And this is just a tiny bit of one of those 10,000 images that we've constructed of this region of the night sky. This is about 5,000 square degrees of the sky, which is about 1/8 of the total sky area that's available to us. Okay. So the Dark Energy Survey is an astronomy survey. We're interested in cosmology, but you can actually do a lot more with a telescope than just cosmology. DECam is a really sensitive precision instrument, and it can find some pretty peculiar things in the universe that are not the things that I'm going to talk about in terms of science. So I'll show you a video here of this moving object. If you can see an object moving in our images over time, it's going really, really fast. This object is 3.5 million kilometers away. And we looked at this on purpose, and I'll tell you why in a second. So the crux of this kind of joke slide really is that DECam is really good at finding things, not only dark matter and dark energy, which is what I'm going to talk about, but if you're having a really bad day and you have no idea where you parked your car, as long as it's more than 100,000 kilometers away, we will find it for you. And so what I just showed you was actually a movie of a car. This is the Tesla Roadster that was launched by SpaceX a couple years ago, when it had reached about 3.5 million kilometers away from the Earth. And we were able to verify that its color was indeed red. Other things that the telescope is really good at is doubling as a seismograph. The telescope and the camera are so sensitive that any tremors in the ground are really apparent in the images. And so you can see, as we were panning in this image here, basically this seismograph recording of how the telescope was bouncing around due to a tiny earthquake in the mountain that the telescope is at in Chile. And the measurements that we're making are in fact so precise, where we're mapping all of these objects in the universe, that we can take their positions as we view them and actually back out what the weather pattern over these 6 years was in Chile above the mountains there. And this is because the path that the light takes through the atmosphere is distorted a little by turbulence due to different weather conditions. And so there's a whole lot of interesting science, fun science besides cosmology that we can do with DECam. But these are not the things that I care about as a cosmologist. And I mentioned I don't really care about these galaxies either. These are not the things that I'm looking for. And I've given you some other examples here of things that are not the things I care about, but they're very pretty and very interesting astronomically that we can find in our images. In particular, my favorite is the upper right, which shows a trio of galaxies that are actually ripping each other apart gravitationally. So these are 3 galaxies that I found in one of our images that are at a very large distance from us, that are in the process of merging together into a single galaxy. But the things that I care about in my day-to-day science are the stuff that's happening in the black images, the dark images, the dark regions of the images. And let me talk about this first, though. This is definitely not something that you want, whether you're a cosmologist or an astronomer. The camera that we use is so sensitive that this is what you get if you happen to look at too bright a star. I mean, no star is very bright to your eye on the night sky, but it's really bad for a camera like DECam. So what I'm looking for, though, is the stuff that's hiding in the dark regions of these images, the stuff that we can't see by eye. And over the last 50 years or so, we have come across some really peculiar things observing the night sky with images like we take from the Dark Energy Survey telescope. One of the first that I want to talk about is what we've observed about how things are happening in galaxies. So if you take an image of a galaxy, like it's shown here, we've noticed in the 1900s, maybe 50 years ago or so, that stars are really moving in a peculiar way in these galaxies. And they're moving in a way that is completely contrary to what we expected from gravitational physics. So if you plotted as a function of the radius, this plot here, from the center of the galaxy, the velocity, the motion or speed of those stars that we observe in the galaxy, you would expect from gravity to see a curve that looks like this dashed one. That is, the motion of the stars would get faster as you go out from the center and then start to fall off. And the way we know this is very similar to this experiment that you might have done as a kid or as an adult, where you fill a bucket of water, you attach a rope to it, and then you just swing it over your head. And if you swing it fast enough, things are okay. If you don't swing it fast enough, you get wet. But the act of swinging that bucket up over your head imparts a velocity to the bucket and the water inside it. And the normal gravitational pull of the Earth that would make the water fall down on you, if it's moving fast enough, that velocity counteracts that force. And the same thing is happening to these stars and these galaxies. There's a gravitational force that are pulling the stars toward the center, where most of the mass is. And the velocity of the stars as they orbit around the center of the galaxy, that velocity is counteracting the pull inward. So if the stars were moving too fast, they would fly out of the galaxy. If they were moving too slow, they would fall into the center of the galaxy, like the water would fall out of the bucket on your head. But if they're moving just right, they'll be in a stable orbit. And that stable orbit is what this dashed curve represents. Now, what we found is something completely different. And this was discovered by scientists called Dr. Vera Rubin in the 1970s, I think, about 50 years ago. And what she found, and others have confirmed since, is that the velocity actually follows this top curve. It rises, but then it keeps rising. And if we were to look at the galaxy and add up all the mass that we see in the stars in the image, that can't happen gravitationally. It's physics nonsense, basically. And so the only way that this picture works is if there's a whole bunch of stuff in the galaxies that we can't see, that we've called dark matter. And in fact, most of the galaxy must be some matter that has gravitational forces, attraction, but we never see in our images. And so this is the first really big mystery that came out of the 1900s in terms of cosmology, what cosmology is today. The other observation, which McKenna spoiled with the intro questions, is that the universe is expanding. And it's not just expanding, but it's expanding faster and faster over time. And we make this measurement in a way that's even more intuitive for you. It's something that you do every night when you drive. So we know that lights of some intrinsic brightness, if they're far away, they appear dimmer than if they're close by. And you can see that with this row of streetlights. The lights further away from us appear dimmer. And you do this calibration in your head intrinsically every time you drive at night. If you see car headlights far away, it doesn't take long for you to calibrate whether the car is coming toward you or going away from you, besides the fact that you know the car's headlights are in the front of the car, just due to whether the lights are getting brighter or dimmer. And we do this on a cosmological scale by looking at explosions, really bright explosions of dying stars that are called supernovae. And we look at these explosions off into the distance in the universe. And as we look further and further away, these explosions appear dimmer and dimmer. and they appeared more dim than we would expect them to be. And so we can infer from that that not only is stuff moving away from us, but it's moving away from us in a really weird way. So if you just had matter in the universe, gravitational mass, you might expect that at some point as you go in time, the size of the universe, the stuff in the universe, this gravitational attraction would eventually pull things back together, just like water falling on your head. Matter attracts matter, and you would expect at some point, maybe that matter would start to collapse again. That's the bottom curve shown here, representing the stuff in the universe over time. But what we found is not only is that not happening, but it's not the blue or the green or the yellow curve either. The universe isn't just expanding, it's doing what this top curve is showing. It's expanding in an accelerating way. And as time goes on, it's expanding faster and faster and faster. And gravity doesn't work that way on its own with normal matter. And so there must be this other stuff or this other thing in our model called dark energy. We call it dark again because we've never observed it directly. And we call it energy because it must have some kind of like negative pressure, something that's pushing things apart, making the universe grow in size. And so we have these two mysteries in cosmology now, dark energy and dark matter, neither of which we can see, but both of which are absolutely essential to explain these fundamental things we've observed over the last 50 years. So now we get to the second question. Why do we care if we can't see it? And this comic is only partly in jest, because in fact, the first astronomical observations that were recorded come from something like 30,000 BC. So we really have, since we were all cave people, been asking this question: where did things come from? What was the origin of the universe? How did we get to where we are today that allowed life to form? And what's the ultimate fate going to be of everything? And this is really what we care about. And the answers to those questions depend crucially on our understanding of what exactly dark matter and dark energy are. And so we really want to understand these two dark mysteries in the universe. If we include these two components in our cosmological model, along with normal matter, we get a picture of the universe that looks something like this. And you may have seen a figure like this before. But the basic picture is that there was a Big Bang, capital B, at the beginning. And so at the start, the universe was much smaller, it was much denser, and much hotter. And so matter didn't work like it works now. You basically just had a sea of photons and fundamental particles in this hot, dense plasma soup. And as the universe expands, it cools off, and this allows atoms to form. And this happens at around 400,000 years after the Big Bang, which is this left side of the plot here. And from that point, the universe gets bigger, mass coalesces together. You get this formation of stars, the formation of galaxies, planets, clusters of galaxies, us. And as you get toward the right side of the plot, eventually the size of the universe, represented by the size of the sphere, starts to expand faster and faster. And this is driven by this dark energy. And so if you were a physicist in the early 1900s, it was a great time. We were pretty sure that we understood everything. Since then, we've kind of dropped the ball, and we're absolutely certain that we only understand 5% of the universe. There's this idiom that it's good to know what you don't understand. You should understand what you don't understand, and we're really good at understanding what we don't understand, not so much yet at understanding what that stuff is. But we've called it these two things, dark energy and dark matter. And so the universe is basically made up of 5% of stuff that is normal matter, like the desk I have, us, the planets, galaxies, stars. Another 25% that is other matter that gravitates, but doesn't interact with normal matter. It doesn't interact with itself. It doesn't interact with light, so we can't see it. But it has gravitation, and it's what causes these observations that we see in galaxies. And then 70% of the universe is this dark energy stuff that has this negative pressure and is causing the universe to expand faster and faster today. And we really need to understand what these two things are. And the reason this is important is that they're intimately tied to how we got here and where we're going now. So on this plot, I'm showing you a simulation of structure formation in the universe. So this white stuff is cluster of mass. You can think of the nodes of this filament as something like galaxies or clusters of galaxies. And you start at the early time in the universe on the left and move forward to the right. And what you'll see is that as time goes on, this mass gravitationally collapses into structure. But how much structure is formed and when it forms depends on how much dark matter there is. There's 5 times more dark matter than normal matter in the universe. So when structures form, when galaxies form, depend on how much dark matter there is. So whether the galaxies form soon enough for planets to have formed, for life to have formed, for us to have formed by this time depends on how much dark matter there is and how it behaves in the universe. At the other end, the ultimate fate of everything depends on what dark energy is doing. So I talked about if you had a universe that was just matter, you would expect a picture like the first progression on the left, where you start at the Big Bang at the bottom in the past. The universe expands, but there's just mass, and mass gravitates. So eventually that gravitational attraction pulls things back together. And at the end, at some point, you'll have a collapse of everything back in on itself. And we call this the Big Crunch, this fate of the universe. And that doesn't sound so great, everything collapsing in on itself, but it's actually the best option of the 3, I think. The more dark energy you have in the universe as you go to the right of this plot, the more strange the end of the universe becomes. If you have enough dark energy, not only will the universe keep expanding and not collapse, but it will keep expanding faster and faster. So if you have enough dark energy, but not too much, then you get into a situation where all of the galaxies are streaming away from each other faster and faster, and eventually we'll be left in the Milky Way galaxy, our galaxy, and everything around us will be dark. All of the other galaxies will have expanded so far away from us that we can no longer see them. And so we'll be alone in the void. And eventually everything in our galaxy will collapse into the central black hole. The mass in that black hole will radiate away with Hawking radiation. And this fate of the universe we call heat death. It's a very lonely situation and kind of sad, but not as bad as the other option. And depending on how dark energy works, we could be in this other situation where, as time goes on, dark energy is so strong, the acceleration becomes so rapid that not even the galaxy can stay together. The stars of the galaxy will be ripped apart. The Earth will be ripped apart from the sun. The planet itself will be ripped apart. Everything will be ripped apart by this force that is dark energy, which dominates at some point all of the other fundamental forces, even at the level of particles being ripped apart. And this is called the Big Rip. And this is probably the one we don't want to end up in, if anyone is still alive at this point. These are all very, very far in the future, though. So none of us will experience any of this. But on a fundamental level of understanding where we're going, understanding these fundamental physical problems is the center of what cosmology is. Okay, so now I get to the fun part, which is we know, or at least our model tells us that these things exist, dark matter and dark energy. And we have to ask, how do we actually know, how do we learn more about them if we can't see them? And so my research is all about mapping this stuff that we can't see. And the way we do this is with gravity itself. So you may be familiar with this idea in general relativity where we model the universe, the space-time that makes up the universe, as this thing that curves where mass is. So mass causes space-time to curve. And the path of light, for example, in that curved space-time causes it to look like light is bending to us. So if you have something like is shown here, a cluster of galaxies, this really massive object in the universe, and there's a galaxy on the other side of it from us, the light from that galaxy is going to pass by this mass. The path of the light is going to bend, it's going to be deflected due to the gravity of this mass, and it will converge back on us at Earth. And so, for example, there are these two orange paths here, and if we looked from Earth out along the left and the right orange path, we would actually see two images of this galaxy because of the convergence of the light from this gravitational lensing. And so we're really using gravity itself as a lens to observe faraway galaxies. Okay. An example of this in real life is shown here, where you see in the inset image these 4 yellow dots where the arrows are. These are actually the same object that we're seeing from different paths of light that are going around this very bright central galaxy here. And this is another example of this that is less extreme, where you don't see multiple images of the same galaxy, but instead you see these very broad arcs. So I'm not sure if you can see my mouse, but just to the upper right of the main central bright area, you can see this tangential arc. And there are lots of these that you can see in the image. And these are the background galaxy images being distorted by this lensing effect. And suitable for astronomy on tap, if you happen to have a wine glass handy, the shape of a bottom of a wine glass is actually the right shape of lens to mimic a gravitational lens. So if you look through the base of your wine glass, you'll see things behind it be distorted in exactly the same way that a gravitational lens distorts faraway galaxies that we observe. So I mentioned, though, that I don't care about these galaxies you can see. What I want to measure is not the distribution of mass in a cluster of galaxies, for example, or a galaxy. I want to understand how all of the mass in the universe is distributed. So I want to know what the lensing effect is at every point on the sky. And so I want to look at as many galaxies as possible. In practice, this is hundreds of millions of galaxies. And so I've made a simulation here to show you how this works. So here I've simulated a bunch of random spherical galaxies that are randomly distributed. These are like background galaxies that we see in the images that we take. And then I've simulated placing a distribution of dark matter between them and us. And what you see of them, their images, is this. Those circular spherical points become this distorted kind of map of shear of this distortion pattern. For mass that is not like a galaxy, it's very dense like a galaxy or a cluster of a galaxy, for the general structure of the universe, this effect is really small. In fact, to make it visible for you here, I've magnified it by 50 times. So if you imagine this pattern, but 50 times weaker, that's what I'm trying to observe in the distribution of the shapes of galaxies that we observe in our images. And due to this gravitational lensing effect, if I know, if I can observe the shape of all these galaxies, I can actually predict what the mass that is between us and those galaxies looks like, what the distribution looks like. Okay. And this is what we're doing with the dark energy survey. With all of these 10,000 images we've taken, we find all of the galaxies in them, we measure their shapes, and we use our knowledge of gravitational lensing of GR to predict what the distribution of all the mass between us and those galaxies look like. And so this is a map of the galaxies that we've measured shapes for in the dark energy survey. The color bar tells you the density. In total, it's about 100 million galaxies and about 6 galaxies per arc minute squared, which probably doesn't mean anything to you. So you can convert it to something more useful by multiplying by about 1,000. And so if you multiply that number by 1,000, you get the number of galaxies in an area on the sky that's the size of the full moon. And it turns out in DES, we have measured in an area the size of the full moon about 6,000 galaxy shapes, and about a factor of 3 more galaxies that we've identified but couldn't measure a shape for. So in total, we are observing about 20,000 galaxies in an area that's the size of the full moon on the sky. This is what this footprint that I just showed you of galaxies looks like in the context of something you might be more familiar with and might even have seen on the sky, which is the disk of the Milky Way. So we live somewhere in the disk of this galaxy called the Milky Way. And so in a ring on the sky that looks like this, you can see the stars from the disk of this galaxy that we live in. And the region of sky that we're looking at is as far away as you can get from the Milky Way's disk so that we are not seeing those stars. And that's this region here. So once we've measured the shapes of all these galaxies, we can do something that is actually really complicated in practice, but is really just backing out this diagram that I showed you of this impact of gravitational lensing to infer what the distribution of mass between us and the galaxy had to have been to cause the galaxy to have the shape that we observe it to have. And when we do this, we are actually able to make a map of where all of the mass in the universe is along these lines of sight to the galaxies that we're observing with the survey. And so this map looks like this. And you'll see there are 3 versions of this because we've had 3 rounds of analyses where we've looked at larger and larger areas of the sky. So where you see a red color, this is where there's more mass in the universe. And when you see blue, there's less mass. And one really cool thing to notice is that in the lower left region, that is common to all 3 of these maps, the same large structures are apparent in all of the iterations that we've done. So we're really measuring real structures of mass in the universe. And in fact, this is not this is not the mass just the mass that we can see. This is any mass that behaves gravitationally. And that's really the key, because dark matter, even though we can't see it in our images, it behaves gravitationally, and so it will lens the matter that we can see. And so this is a map of dark matter in the universe, the stuff that we can't see. Okay, and so now I'm going to come to the final question, which is, now that we've mapped out where the stuff is that we can't see, what can we do with that information? Okay. So if we go back to this picture of the universe, we have kind of 2 special time periods. One is on the right, which is this region of the universe that we can observe with the dark energy survey. The other is the very beginning of the universe, this time 400,000 years after the Big Bang, where the cosmic microwave light comes from. We call this the cosmic microwave background. This is light that's coming to us from the moment when atoms started to form at the very beginning of the universe. And this light from the CMB, the cosmic microwave background, allows us to map where matter was, the distribution of matter at that point in the universe at the very beginning. And we can produce a map that looks like the upper left figure here, which is these perturbations in the density field at this period at the very beginning of the universe. But we also can observe where galaxies are. We can use this gravitational lensing to build this map of dark matter much further along in the universe's evolution with the dark energy survey. And so we're able to both observe how mass is distributed at the beginning of the universe, but also fast forward more than 6 billion years to the time that we're observing with the dark energy survey and re-image what the distribution of mass in the universe looks like. And that is the map that I showed you. And so what we can do is we can take the observation from the start of the universe, and assuming we understand what we're doing, assuming our cosmological model is right, we can fast forward that map. We can predict how it will evolve over time until we get to the time period that we observe with DES, which is represented by this simulation image in the lower right here, which represents the structure of dark matter. The structure is much clumpier. There are actually real structures now in this late time that we can observe, things like galaxies and stuff that didn't exist at the time of the CMB. The physics that are happening are very different. At the beginning of the universe, you're in a hot, dense plasma. We're observing galaxies and mostly void in the late universe with DES. But we should be able to say, given the measurement of the CMB and our cosmological model, if we fast forward 6 billion years, this is what we think the universe should look like. And we can ask, is what the universe that we're actually mapping with gravitational lensing the same as what we predict it should be? This is a fundamental test of the cosmological model and really our understanding of physics as a whole. And interestingly, so far, things seem to look okay. They look pretty similar, what we are predicting from the beginning of the universe and what we're observing. But they don't look exactly the same. There are some small differences that are becoming more apparent as we make larger and larger of these maps that I showed you. And so the interesting question, I think one of the most interesting questions in cosmology in the next few years, or even the next decade, is going to be, as we make these larger and larger maps of dark matter today, will we find that it really is the same as what we think it should be from the CMB? Or is it not? And if it's not, then something about physics, something about our model of the universe is wrong. And how different it is may tell us something fundamental about our understanding or misunderstanding of what dark matter and dark energy are doing. And that's one of the key things that we're trying to understand right now as cosmologists. The other exciting thing about cosmology right now is that we're entering the end of these surveys, like the dark energy survey, that have been going on for the last 10 or 20 years. And we're getting ready to kind of pass the scientific baton on to the next generation of experiments that are basically 10 to 100 times better in every way that you can imagine. And so these experiments include the Nancy Grace Roman Space Telescope, which is going to launch in 2025 or 2026, and the Vera C. Rubin Observatory that is on a neighboring mountain to the Dark Energy Survey's camera in Chile. These are the US-based missions. One is a space satellite, one is a ground-based survey, and these are going to really revolutionize what we're able to do in ways that DES just can't. And so it's a really exciting time, especially for the group at Duke. We're really leading efforts for both of these projects to prepare for cosmological science in the late 2020s. And an example of this is this image here, which is from the title slide. This is a 0.01 square degree simulated image of what we think we'll be able to see with the Roman Space Telescope that our group here at Duke has made. We make these simulated images to prepare for the actual data that we'll take with the experiment to test our methods and develop our measurement pipelines on. And this is an example of the work that we're doing at Duke. To give you a sense of how tiny 0.01 square degree is, you could fit 1,000 of these images in the area of the full moon on the sky. So you can imagine just how many more galaxies we'll be able to see with the Roman Space Telescope than we can with DES. So it's a really exciting time in cosmology. And as we prepare for questions, I'll leave you with this video of how the Roman Space Telescope might observe the sky that went into creating an image like the one that I showed you here. So thank you very much for listening to me. I hope you learned something about the dark night sky that you didn't know before. Thank you for having me.
Thank you. That was an excellent talk. That was incredibly interesting. We already have a couple of questions in the chat. So anyone else, if you have any other questions about Dr. Troxell's talk, go ahead and put them in the chat. But I'll get started with the ones we already have. So Fred asks, so if the end is the big rip, will everything end up as elementary particles, all completely separated, the opposite of state of being just before the Big Bang?
Yeah, so there's basically this balance of forces that come into play. We have the fundamental forces that hold atomic structure, the stuff that makes structure possible. The strong force and the strong nuclear force and the electroweak force. And then you have gravity. Gravity is much weaker than the other forces. And in a tiny region of space, dark energy is also much weaker than them, which is why, for example, you're a structure. You're not being pulled apart right now. The weird thing about dark energy, though, is that its strength grows with the size of space. So as space gets bigger, dark energy gets stronger, and that is causing this acceleration of the expansion. And it's kind of a runaway thing. And if dark energy has certain properties, if it's strong enough in a sense, eventually these regions of space become large enough that these forces overcome the other fundamental forces. So first it will overcome gravity. So bound gravitational structures like galaxies or even stars will be pulled apart. Then it will overcome the electroweak force. And then finally it will overcome the strong force, which is what holds the nuclei of atoms together. And so you would be left with this quickly dispersing kind of cloud of fundamental particles at the end after all of these forces have been overcome.
Wow. Okay, so the next question says, so I may be wrong, but I interpret the collapse of galaxies over time, forming galaxy clusters and filaments, as a decrease in the apparent entropy of the visible universe. Does dark matter or dark energy have entropy, and is it taking it away from visible matter?
So that is an interesting question. The way I would think about it is that in almost all respects, dark matter is like normal matter. The way it interacts with other particles is different, but fundamentally it should obey the laws of thermodynamics just like normal matter does if you account for these differences in interaction potentials. Dark energy is a kind of another beast altogether. So it could be something that is a thing, some energy that has this negative pressure behavior. But there's another possibility, which is that it's just a fundamental constant of nature. So understanding really in particular which of those two things it is one of the most burning questions in cosmology right now. Because if it is a fundamental constant of nature, like the gravitational constant, or the strong, the fine structure constant, then it is what it is. And it's kind of outside of dynamical questions like thermodynamics. But if it's a thing, if it's in some energy or fluid that has this negative pressure, then it must interact in terms of pressure and thermodynamics, just like all the other matter does. And so it really depends, I think, on what the fundamental nature of dark energy ends up being.
Neat. The last question we've got so far is from Fred. He says, is there any known correlation between lensing and a redshift?
Yeah, so you saw redshift on some of my slides, I'm sure. And I try not to say it in talks that aren't technical because it's a little, it's not a normal kind of measurement like distance or time. So basically, because of the finite speed of light, in cosmology, astrophysics, we usually talk about time in the same way we do distance. And I kind of did that when I was talking about the difference between the CMB and the part of space that we observe with the dark energy survey. As you go away in distance, it takes light longer to reach you. And so you're actually looking backward in time as you look further and further away, which is why we can see the beginning of the universe in this cosmic microwave background radiation. And so redshift is another way of measuring distance. Because the universe is expanding, the redshift increases. The redshift of the light that we see increases, kind of similar to the Doppler effect that was mentioned at the beginning, but not quite. And so as you go to higher redshift, to larger redshift values, you're moving to distances further away from us. And there is a strong correlation with distance or redshift and the strength of gravitational lensing. So it's not apparent in the figures that I showed, but the strength of the lensing effect depends strongly on the relative distance between the object or mass that is doing the lensing, the observer, and the structure that is being lensed. And there's some balance there where the strongest effect happens when the mass is kind of equidistant between the observer and the thing that they're observing. But in general, as redshift or distance increases, the lensing signal also increases. And so if we take something, there's a statistical measurement we use called a correlation function, which measures basically how likely it is for two galaxies at a given distance to have the same lensing, the same distortion in their shape. If we take that as a function of redshift slice, we cut up the galaxies in our survey in slices of redshift or distance, we find that that signal, that correlation between the shapes increases exactly with redshift.
Cool. Here we have a follow-up question on the entropy question. If dark matter has an entropy, does it also have an analog to temperature?
Yeah, so I'm not right. So this is I don't have a good answer off the top of my head, and the reason is that the way we model dark matter is that it is non-interacting even with itself, and so there is no pressure in a collection of dark matter. And so I'm not sure how you would translate that to temperature off the top of my head. I think I'll leave the answer at that.
A question for the future then. Here is another question. So in a recent paper, the authors presented the result of a simulation about the filament structure in the universe, remaining proportionally constant, whether scaled up or scaled down. Can you comment?
So this is basically the idea that the correlation amplitude is scale independent. That is another technical way of, I think, of saying what you're asking about. So the way another way of describing this is through something like this correlation function that I mentioned. So in terms of this statistical language of the correlation function, let's talk about galaxy positions. So if you look in your survey and you count all the galaxies at a given distance away from each other, and you ask how many galaxies do you find at that separation from each other if you take and count all of the galaxy orientations, the number of galaxies that you find relative to what you would find if everything was homogeneously distributed, randomly distributed, is the definition of the correlation function. And so the correlation function is telling you what is the likelihood of finding a pair of galaxies at some separation relative to random. So if you have clustering structure in the distribution of galaxies, like we do, like you see in this image, then there will be scales where the correlation function is positive, is greater than 1, not greater than 1, positive. And what we find is that there is a scale dependence to that on the scales that we are probing with dark energy survey. So these are scales that are something like between 1/20th and 1 degree, or 2 degrees, 1/20th of a degree to 2 degrees on the sky. Within that, there is a scale dependence to the correlation function, but this is a measurement in angular space. And so you have to convert that to a measurement in real space, which you can do. But there is a scale dependence to the what we call then the power spectrum in real space. So I think that we are measuring some difference as a function of scale in the clustering amplitude.
Yeah, that's really interesting. I am not seeing any more questions at the moment. We'll give everybody a couple more seconds if they have any last questions. But yeah, thank you very much. That was an excellent talk. I had a thought in my head and it left. So we'll see if it comes back before. Here's a question. Does dark matter or dark energy give us any clues to entanglement?
Like quantum entanglement?
I presume that's all the question says.
Okay.
But
so quantum entanglement, if that's what we mean, is the consequence of the interaction of a wave of a wave function of a particle with some potential of two particles with some common potential, most usually, and it basically entangles the wave functions. That's a general thing that happens in quantum mechanics. And so any particle that could be described in quantum mechanics would be subject to entanglement given the right conditions. The scales and energies that we talk about in cosmology are very far from the quantum scale. And so there's generally not, except in something like the interior of stars or black holes, neutron stars, quantum mechanics doesn't play much role in the large scale structure of the universe. I have also lost what I was about to say. There is a complication at some level in that a lot of the description that this idea of dark matter and dark energy is built off of relies on general relativity. And one of the outstanding questions in physics is how to reconcile quantum mechanics and general relativity in a unified theory. They work very, very well in the different regimes that they're responsible for. And so if we were able to isolate a particle that corresponded to dark matter, which we haven't been able to do yet, then, like I said, I would expect that particle to be as subject to entanglement as any fundamental particle is. But as it is, we have not been able to identify any particle or fluid component that of what we would think of as normal matter that actually corresponds to dark matter and dark energy, which are phenomenologically something that arise from this model of general relativity that we use. So it's possible there is a fundamental disconnect, but this is at the level of where we are in physics as a whole, and that we haven't bridged this gap between quantum mechanics and general relativity yet.
Cool. Yeah, that's one of the big questions is how do those two come together? Here we've got another one from Fred. He asks if there is If there are explanations for redshift other than correlation with distance, for example, if gravity has a bigger impact than known, how would the model change?
Okay, so one of, I guess, something that is close to what you're asking that is fundamentally interesting, I think, in the vein of your question, is that this description that I've given you of dark energy and dark matter assumes that they are part of GR, that they fit into the theory of general relativity, and that general relativity is right. There is a large part of cosmology, modern cosmology, on these scales, and in this study of large-scale structure and other probes of cosmology studying dark matter and dark energy, in particular dark energy, that question, in fact, whether GR really is right. We have so much evidence that GR works, but all of that evidence is on much smaller scales and much smaller energies, much smaller time scales than the universe as a whole. So we know GR works on Earth. We know it works in the solar system. We know it works for compact bodies in the universe, like binary pulsars. But whether we can really extrapolate that hundreds of orders of magnitude to the entire universe and across the whole age of the universe, we are not able to prove that yet. And so part of this test that I talked about, comparing the early universe predictions to what we actually see, one resolution to that, if we find that they don't agree, may be that GR fails on these large scales. And then gravity would perhaps need to be modeled differently. And that could also be an explanation for what is happening with dark energy. Maybe it's just that GR is wrong, and there's some other modified theory of gravity that would account for what we see without invoking something like dark energy. And trying to understand if that is a real possibility, or even the real universe, the real physical theory, is an active area of study in cosmology.
Great. Yeah, there are. What I'm getting from the answers to your questions is that there are a lot of open questions in cosmology.
Yeah, I mean, if you want to get into a field where we don't understand anything and everything is open, cosmology is the one. It's a really exciting time to study cosmology, particularly with these next generation of experiments that are starting to take observations in the next couple of years, that will really allow us to test things at a level that we've never been able to test before.
Yeah, this simulated image is insane. That's just so much detail. I'm not seeing any more questions from the audience though. So I think we will wrap up for the night. Thank you again for the wonderful talk. And for Astronomy on Tap, we will see you guys next month for our next talk in March, which I believe will also be the 2nd, March 2nd. So thank you everyone for coming, and we'll see you all next month.
Thank you.